Thank you so much. I have to apologize in advance for my lost voice, which I regained about 30 minutes ago. So if I lose it again, please bear with me. I may have to stop and whisper maybe. Can you actually understand what I'm saying? No? Fine? Right. I have to maybe apologize to those of you who know my story. You'll see some slides you've seen before, and some of you will have seen some glimpses, including in the talk I gave not so long ago here in this auditorium. But to me, shifting from many years of auditory research to actually presenting language visually has been a major step, even though it wouldn't look like that to you. So the work, even though I'm now representing Center of Functional Integrative Neuroscience in Aarhus in Denmark, since a few months ago, the work was actually done in Cambridge, in Helsinki, and in St. Petersburg, what I'm going to talk about. So the question that already arose in some of the previous talks is to what extent language is automatic, or whether it draws on some attentional resources. And the ease with which we can perceive the entire complexity of language has prompted suggestions that this function is to a large degree automatized. And this automaticity has been so far suggested for practically all levels, from phonological analysis to lexical, morphological, semantic, syntactic levels, all the way up to the level of dialogue. And as we were walking this morning here, I was whispering to Andrea and Alexander about some studies done in Aarhus where when people communicate, their heart rate becomes synchronized. So this automaticity and which happens automatically, obviously, you don't consciously control that. So it permeates different levels, but today we'll only talk about single word processing, that is lexical access. And something that we used repeatedly in sort of 12 years ago in the beginning of this research program to look into this is to present spoken words in auditory modality when subjects are not paying any attention. And in these first studies, we used just a few words which were presented in unattended oddball paradigm and used mismatch negativity as a measure of choice. And I'm very glad Taya yesterday introduced the MMN response in great detail, so I don't have to do it now. And what you see what it happens when you listen, when you're actually not listening but just hearing to the words and pseudo words that have been played to you and you're doing something else, you get this solid increase of word-related response over pseudo words. This is MEG data, but you also get it in EEG and fMRI as well. And importantly, since this is not a very natural paradigm, oddball design is not something we use to communicate with each other every day, you can find the same effect when you present stimuli that are not repetitive, that don't have oddball paradigm, but as long as you match their acoustic properties, such as in this work by Lucy McGregor and colleagues, which we published a couple of years ago, we presented more than 100 of acoustically and psycholinguistically matched words and pseudo words, and we found the same phenomenon. We found that the brain reacts more strongly to unattended spoken words than pseudo words. The dashed line is pseudo words. Throughout this is just a global response of the MEG signal, and you can see how this activity can be modeled in sources that in temporal, inferior frontal, and precentral areas, gradually spreading in time from 50 milliseconds up to 420 milliseconds, spreading to inferior frontal areas. So this enhanced response specific to lexicality as the property of stimulus can be elicited when attention is withdrawn from the stimuli and there is no stimulus-related tasks. And importantly, it's observed when you balance carefully the acoustic, physical, phonetic properties that are the biggest variable that influence your responses. We've seen it in dozens of mismatch negativity studies, which were replicated by groups in different countries. And we've also seen it in non-mismatch negativity, in multi-item designs, as I've just shown. And this enhancement has it was repeated in many papers, is best explained by activation of long-term memory traces. So you automatically activate a memory trace for a word when you hear it, even when you don't pay attention. And you start this from about 50 milliseconds after the information arrives. So the take-home message from these background studies is that the spoken word processing is rapid and automatic. And why would that be like this? And the reason for that is whatever you have as a representation for your word, as an entry in your mental lexicon, must be a very robust thing. It's likely a robust neuronal network that encoded the words a long time ago and gets activated robustly and strongly every time you're presented with this word, even when you're not paying attention. There is no such representation for a pseudo word, therefore there is no activation to the same degree. Now, of course, when we make this suggestion of word memory traces being distributed circuits that are robust and automatically activated, then there should be no reason why this is only true in the auditory modality. And therefore, we could hypothesize that this account should predict automatic activation of word memory traces in any modality, whether it's auditory or visual, or perhaps even some other modality, if you think of maybe blind or deaf people. So, but at the same time, experiments in the visual modality have not been able to test this prediction, as usually it's difficult to present a visually unattended word. If it's something that you're looking at, it's automatically in the focus of your attention. Now, there is a whole body of research done with masked visual stimuli, when subjects may not be aware that they've seen a stimulus, but there is an important difference. It's usually a word or pseudo word or something else that's flashed in the center of the screen where the subject is paying attention to, and then there is a mask that covers the same space just a few milliseconds later. So you may not be aware that you've seen it, but you are still paying attention to it. So it's not exactly the same thing as the finding that we had in the auditory domain. So what we did, and this is the first of the studies I'd like to show, was actually done here at the Department of Neurophysiology on the other side of the river by my master's student Galina Garyanova, who with the help of the team here, tried to implement the design we previously used in audition in the visual domain. So this is closely following the most bog standard lexical MMN study, where you have multiple standards and a few deviants, and we control the contrast, so the contrast between the deviant and the standard is always the same, but they are the lexical words or they're the pseudo words, and the subjects are distracted from these stimuli. So what you have here is this central stimulus, which is a combination of different circles, like presented here, of different colors, and in each block the subject is asked to detect a certain color combination. So if they ask to detect inner green, outer red, then this is the only right target. The reverse would not work. Outer green, inner red would be a wrong answer. So this is a so-called dual task, when you have to keep track of two features, both colors and locations. And this was well shown in the attention research on some other aspects, that when you have to trace two features at once, this really restricts your attention spot. That was shown by John Duncan and others, for example, really restricts your attention spot to this location. And these things were present there all the time, just changing with, I think, every 900 milliseconds or so. At the same time, 2.5 degrees from the center, these words were flashed for just 100 milliseconds. So there was no time for subjects to saccade to them, and to reduce saccades, we presented them symmetrically on the left and right sides. So actually, many subjects did not report seeing the words at all. So what we had were these different combinations of words and pseudo words. The critical thing is the contrast between the standard and deviant stimulus is always the same. It's K versus N, and it's phonetically the same as well, since Russian is more or less transparent. So you get tok ton, mok mon, And so some of these are pseudo words and some of these are words, and it's all combinations, standard words, deviant words, and all possible reiterations. In addition, we had stimuli that made no sense but included the same contrast, so these hash mark ampersand K, hash mark ampersand N, and finally a separate condition where we only had the circles and no orthographic stimuli. So, and this is the result of sort of global, this is just 30 channels of EEG. This is just global activation, which showed 3 main peaks across all electrodes at times which we know from previous attention visual language research. At 100 milliseconds, you always get a response to visual stimulus. At 250, you have something that's been linked to orthography processing by various groups, most prominently by the group of Manuel Carreras. And finally, you have something in the 400 millisecond vicinity. And this, what we did here was remove the baseline condition. So just the circles condition is subtracted from the orthographic conditions to remove the global visual activation, because of course most of the activity is caused by these huge colorful shapes, not by the tachistoscopic words. And then we started looking at these main peaks to see how they differ for different stimulus types. And what we see, much to, which is what we predicted, is a larger activation for meaningful words as opposed to matched pseudo words. You see a huge peak that's then repeated again and again with time. And in the earliest peak, there is no difference between words and non-words. You can see that later, and these are unattended and unnoticed words and pseudo words. There is later a difference where pseudo words start eliciting activations similar to words, and non-words already are possibly suppressed, not analyzed. Right, and then the other, of course, thing to look into in such a design is whether we get what's known as the mismatch negativity. And there is a visual analog of the mismatch negativity, which was previously shown with like moving lines and circles, simple stimuli. And here we see that yes, we can elicit in the same way as before. As this anterior negativity, this is deviance minus standards, and this is the subtraction. So you see frontal positivity accompanied by left lateralized negativity, which is more or less a standard signature of a visual MMN. Even though we see this, and it's significant in the first two peaks, interestingly, this does not interact with the lexicality. So we saw it for all stimuli, and at the same time, we didn't see that standards or deviance were sort of differently reflecting lexicality. So what we see is a visual analog of the lexical ERP enhancement, here for the first time, unattended written words producing larger brain responses very early on than pseudo words. We also see visual mismatch negativities for the first time seen for orthographic stimuli. However, unlike the auditory modality, we don't see specificity of these responses to words or pseudo words. So in the auditory modality, we specifically see MMN enhancement, and here we see lexical enhancement for both deviance and standards, accompanied by discrimination, MMN in addition. So there seems to be a high degree of similarity with the early auditory research, suggesting similar or even a shared mechanisms of unattended language access in both modalities. And these early and automatic lexical processes of visually presented language seem to take place very quickly, very rapidly, outside the focus of the visual attention, under strong distraction from the linguistic processing. Of course, with these 32 channels, EEG, we couldn't do much about the brain sources of these effects. So we did, in parallel to this, we did a similar study in Cambridge using MEG, and that was done primarily by Claire Cook and Lucy McGregor, and was subsequently analyzed by Francesca Carota, whose results I'll show in a second, where a similar design was used. Again, all possible combinations of the same visual and also acoustic contrast, always T versus R here, but different combinations of standards and deviants being either words or pseudo words. And now they had to detect a combination of colors located one above one each other, and the stimuli were in perifoveal 1.5 degrees from the center space. Now, again, we started sort of being agnostic to what could come out of this. We started by pulling all channels together and just analyzing global responses. And again, we got something distinct from the previous design, but not that different responses, starting from 100 and then dying after 250 milliseconds out. When we looked at this in signal space, and this is just to remind you what it says, it's the brighter the color, the stronger the MEG field, and you're looking at this helmet space from the left side. We see that already early on you have this visual analog of mismatch negativity. Interestingly, the first and the strongest response is already in the frontal channels, not in the occipital ones. And then it sort of keeps circulating, comes back to the occipital channels. And these are all significant results in signal space. These are T values. Actually, these are not activations, these are T values. And when we look at lexicality effects, again, starting from this very first peak at 100 milliseconds, we see a strong significance of enhanced word over pseudo word response in temporal occipital sensors, already creeping into frontal sensors, and this process goes on for longer. So in the source space, I'm not sure you can see the colors, but the upper line is, again, just mismatch negativity, and lower line is lexicality effect. So the brighter color is stronger deviant than standard response. And you have this for the orthographic differences in most significant, these are T values, again, not activations. So the brightest doesn't mean this is the biggest overall activation. Of course, the biggest activation is in your visual areas, but the biggest differences are not, the most significant differences are not. So for the visual mismatch negativity, we get already here Broca area, BA 44-45 involved, as well as motor regions, and superior and posterior temporal regions between 150 and 240 milliseconds. And the lexicality differences in source space start later than in signal space. We couldn't see them at 100, but we could see them here at 180 milliseconds, again in left inferior frontal areas, and later around precentral regions. So of course, these two studies are subject to the same confound I mentioned in relation to the early mismatch negativity work, which is this is not a typical way you deal with language. You don't typically see stimuli that are repeated hundreds of times in such a design. But I must say that in itself, it's not such, the way these unattended stimuli are presented, it's not so untypical. It's sort of what you often face when you're looking at something on a bus and you see the advertising flashing on the side. It may not be in the focus of your attention, but you're exposed to such things all the time. But what is unnatural is the repetition of the same few stimuli, although I must stress that the key thing there was to control these tiny features, like have exactly the same contrasts, have them matched for psycholinguistic factors, and so on. But finally, we need to do something that's more valid ecologically. So we repeated this study together with Lucy McGregor in Cambridge to expose our subjects to, again, over 100 words that are matched for various properties with a similar group of pseudo words, and each one is only played once. And subjects are again doing this combination of spheres detection task, which is non-linguistic, doesn't encourage language processing in any way. What we get then is a difference that starts very early on, and these are MEG responses. Here on the bottom is the temporal channels, and these are the maps of the differences. So The first difference occurs at 90, again the same times at 90 milliseconds in temporal lobe. You see this, or in temporal sensors, you see this increase for meaningful words as opposed to meaningless pseudo words. This is how it looks in time here. Just 60 milliseconds later, this difference has moved to inferior frontal sensors further here on the left. So you have this transfer of information going on quite rapidly in the same non-attend design. Later, and only later, the difference inverts, and then you see already a larger pseudo-word activation at 230 milliseconds in temporal sensors. In source space, and this is preliminary source spaces, since putting this picture together, we've also done statistics in source space, but just to say that in source space, we seem to see a constellation of occipital, temporal, including inferior temporal and anterior temporal, and finally frontal sources underlying this enhancement. So, we replicate our finding of lexical differences in unattended design when words, hundreds of words and pseudo words being flashed at subjects who are not doing anything with them and are doing non-linguistic tasks. At the same time, we find the same time course of events. So the brain seems to, I'm finishing with conclusions, the brain seems to differentiate unattended orthographic stimuli very rapidly after stimulus onsets. We can see it as a mismatch negativities for orthographic stimuli, or for any orthographic stimuli, even if they're meaningless. But in addition to this, we can see that the brain dissociates meaningful written words from meaningless pseudo-word inputs, which also happens very early on when subjects aren't paying attention and the task itself does not even encourage linguistic processing. So it's not like in a study that, for example, mentioned yesterday by Ishton Winkler, when subjects were listening to sounds and were distracted by a book, which is still perhaps could be pre-activating linguistic input. Here, subjects are doing something completely irrelevant for language. And yet, we seem to see that the language system is activated. And it's activated in the form of occipitofrontal network, which must be then underpinning this automatic word recognition process. This automatic process of lexical access could therefore be a supramodal neural mechanism, as we see it in both visual and auditory modalities, and it must be shared by these modalities. And these early stages, which you can see for unattended stimuli, should be the earliest processing stages of linguistic information taking place before attentionally dependent processes come into play, which we know from other studies happens 100-200 milliseconds later. I'll need to thank all the people who were involved in this work, Kalina and Anna here, Clara, Lucy, Francesca and Martin in Cambridge, Sergei here, and Sergei and Alex from here as well, and Medical Research Council for their funding. They funded me for long 13 years. Russian government, Ministry of Science and Education funded the work done here, and European Commission has also provided a lot of generous support, and of course many others. And thank you for bearing with my voice for the last 20 minutes.
Right, questions? One here.
Thanks for the talk and for doing this effort. I've got one question and one comment. The question is, didn't you directly compare the full attention and inattention conditions? Because actually we did it for the word superiority effect, and it turned out that in full attention, words are similar to pseudo words and non-words differ. And inattention condition words are separated from both pseudo words and non-words. I mean, yeah, so you get it.
That's exactly true. So this is exactly what there is. We haven't done this in visual modality, although one of these experiments has also an attended component, and it's preliminary, but we seem to be seeing exactly what you said. That is, and what we see often, most often, is that words, the earliest peak of activation for words doesn't change with the task. It's the same, but it's the pseudo-word activation that changes. When you start paying attention, then it grows, and depending on the amount of attention you give to it, it may reach the same level, or it may even go up, go higher. And the explanation is, of course, you have those memory traces, they become active, and they're just active at ceiling, at least in the first 100, 150 milliseconds. Pseudo words don't have those traces. They don't activate, therefore in non-attend conditions they have reduced activation. However, as soon as you start doing something to them, paying attention, then something comes into play. Perhaps you're trying to find possible explanations, or perhaps their neighbors get activated in the cohort model way of thinking. You activate multiple neighbors. They're never fully activated, but there could be many of them, and therefore then the activation goes up.
Okay.
Hey, so it's a really interesting. So you've made this point about these effects occurring under the threshold of language processing, or that language processing isn't involved. But I guess there is kind of a linguistic component here, in the sense that, if my brain's seeing something that has stimulus features that make it look like a word, the expectation is that it's going to be a word, right? Right. If I'm in a context where I'm supposed to see a word, I should see a word. If you're looking at a sign, there's something that's there and it looks like a word. So I guess the question I have is whether or not, especially I guess you could do this in your MEG data, whether or not you could find something that looks like an adaptation effect. That is, hey, I'm in this context where seeing things, they should be words, but over the course of the experiment, you're going to learn to downweight the expectation that you're really going to see a word. And if that's the case, then you should be able to pull out some nice kind of learning effects, which would support your story, I think.
Yeah, I don't have a direct answer to your question, since this hasn't been tested as you are putting this, but of course you're right in both ways, that there should be some prediction, but we still measure timing from the point in time when the information is enough to differentiate what you're getting. And what we seem to see, like when we have this highly predictive design, the mismatch negativity design, when you have, type, then we have a robust effect about 120 to 200 milliseconds. As soon as we moved to a less predictable design, where we had 100 of words and 100 of pseudo words mixed randomly, we have that. And in addition, we have something coming up at 50 milliseconds. So it seems like in repetitive designs, you have habituation, which is removed in these non-repeat designs. And when sort of investigating this, what you just mentioned, investigating events across the course of one block, I think I saw, but it didn't come out as significant, that in the earliest sort of trials, these effects are much earlier than later. And we've now run, although unrelated to, not the visual study, but Lili Kimpa in Helsinki, a PhD student whom Tei and I co-supervise, has done a learning design with multiple words and pseudo words and non-words all mixed up, and she found strong learning effects at 50 milliseconds.
Yeah, just point of clarification, because I'm curious. With the properties of the MEG signal, you could feasibly do some sort of continuous trial-by-trial analysis where you don't need to bin, because binning it sacrifices a large amount of power, especially because these are early effects.
You might be pushing. We might be pushing it with trial-by-trial, but I think maybe the tens, dozens of trials at once would probably go work.
Okay. Do we have more questions?
One problem I have is, what do you mean by automatic? If a stimulus hits the retina or the eardrum, it's obligatorily, it's going to just propagate through the system to some extent. And then that's automatic, I guess.
That's automatic. And
when does it stop becoming potentially automatic in that sense? How much room for manoeuvre does a Does the actual
Well, I think the
processing
key
system
thing,
have?
maybe yes, everything is automatic in a way, and I usually carefully say that it's automatic in a sense that it doesn't require focused attention. That's sort of a very broad distinction. So you don't need to concentrate on language input, or in fact to be conscious of that, to process it as such.
Right. But if I say to you, the red dog, right, and you say, well, is the processing of that automatic or not? It seems to imply that you envisage a possible world where I hear the and red and dog, and I don't try to integrate it into a phrase. And it's only because I attend to it or I wish to interpret it like that that I can achieve that phrasal representation. But you don't mean that, do you?
No, I don't mean that. I think I mean something more basic, like I've just described. And in fact, you also seem to parse things automatically very early on and combine them in the same way. But later on, if you look at responses that start accumulating after sort of 150, 200 milliseconds, they strongly depend on attention. And so, including N400, for example, which almost disappears in non-attend designs. So to actively understand that these, he has his tea with milk and socks and sugar to actually understand that this is wrong, you do need to focus to allow more resources, which probably means disinhibit the relative areas and allow more resources for them to analyze the input, maybe reanalyze, reparse the input again.
Right.
I don't think we've agreed with
Do we have more questions? I actually have a quick one before you go. So these words that you show people compared to pseudo words, did you test whether they are later available for conscious access by means of, I don't know, recognition, accuracy or something like that?
In most of these experiments, we ran questionnaires
Yes.
on subjects, and not in all, but especially when the first experiment, when they were presented parafoveally, so further 2.5 degrees from the center, it was something like 9 out of 16 didn't report seeing anything.
Well, that's a different question altogether.
Well, I mean, what they think of them. Yeah, they rate them as meaningless or meaningful, even after being exposed to them.
So they're better, their accuracy. So for example, if you show them in a list of words, will you have any implicit signature of them recognizing this stimuli?
Have not done that. No, have not done that.
That would be, kind of a little toward the direction of where it's automatic, where it actually enters the processing stream,
Right.
and where it ends. I mean, this is just a reflex. I know you use this metaphor a lot, that it's a reflex. But then, does it allow access to meaning?
I should correct myself a little bit. We actually did a study like a kind of what you suggested when subjects with Max Gargnani and Matt Davis in Cambridge, but that behavioral study was linked to fMRI experiment where we wanted to see how these things are learned and how many trials you may need and whether it requires attention. And it seems like when you really bombard subjects with many trials, like 200 trials, without having them attend to them, they're still better at, it interferes with their lexical decision task the following day. If you don't bombard them with many, then it doesn't. I think that's my memory of results, which still have to be analyzed.
All right.